we now get to the Kalman filter itself. And we start off with what we call the system model. This is what we start with. It's how we're modeling our system. It is a discrete time state space. This first equation is called the process equation. This one is called the measurement equation. The W and the V are random variables, random vectors. This W is called the process noise. This V is called the measurement noise. And we're assuming throughout this that the means of these noise terms, these random vectors, the means are zero. At any given time step, we know they are covariance matrices. And they are white or independent sample to sample, meaning the W at time J and time K, if they're two different times, they're uncorrelated. Same for the measurement noise. It's uncorrelated from time step to time step. It's white or independent sample to sample. And the W and V are uncorrelated from each other. So that's the setup of the system. And then we're going to apply the blue process, best linear unbiased estimator, using that recursive way of doing it. To kind of keep, believe it or not, I'm trying to keep the notation simple. The hat means the estimate. The K means at time step K. If it has this little superscript dash or minus, that means remeasurement. So this is our estimate of the state at time K before we process the measurement we get at time K. Remember, X is the state. State variable state space thing up here. And same way here. P is the covariance of the error of our estimate at time K before we actually processed the measurement at time K. Once we process the measurement we get at time K, we get rid of that superscript. Okay, now let's get into our blue method. Imposing linearity in a recursive format, that means it's set up like this. Our estimate at time K is the estimate we had prior to getting the measurement at time K, plus this correction term. This H times X here, that's really what we expected to measure. Z is what we actually measure. And then this K weights the sort of difference between how much we trust our previous estimate versus how much we trust the measurement. K is the gain. By unbiased, we mean this. We mean this expected error between what we estimate and the true state. That expected error is zero. That's what unbiased means. But let's look at it. Here's what we have by our linearized model. Plug in the Z for what it is from our measurement equation. And let's see. Yeah, that's all we did there. We plugged in for C. Now let's subtract off X sub K from both sides. That's all we're doing going from here to there. After this line, we'll start grouping terms. We have this X hat minus this X there. We can pull out the K and the V on its own. And then these two H terms, we can pull out the H. And we have an X minus X hat. And then these two terms are the same, so we can combine them again. We have an I identity matrix minus that KH times that. And now when we take the expected value of everything, Well, the expected value of the V by the system model, 0, so this guy. And what about this? Well, if our estimate prior to processing the measurement was unbiased, then this is 0. And then the whole thing is 0, so that our estimate post-measurement is also unbiased. And in a little bit later, we'll show that this is truly unbiased, which means if we were unbiased before we process the measurement, we'll be unbiased after we process the measurement. Now let's look at that error, because we want to look at the covariance of that error. Here was the error. We got that in the previous chart. The covariance by definition was this thing. And what is that? Let's replace each of these guys with this mess. So this becomes this one big long expectation. What we're going to do, like high school algebra, we're just taking sort of two parenthetical terms and doing that by the first terms, the first and last, then the inner terms, and then finally the last two terms. So let me go from here down to here. The first thing we do is this upfront term here times this guy, but the transpose of this guy. And this is the result of that. I'm not going to go through the matrix arithmetic so much. You need to know how to treat transposes, etc. Then the cross terms, this upfront term times this KV, and then this KV times this upfront thing, they're going to be 0 because it ultimately comes down to this. This is 0 because our estimate prior to processing the measurement at time K is uncorrelated with the measurement noise at time K, right? Because this with the minus sign up there means before we process the measurement, and this is the measurement. And because of this, the true X has nothing to do with the measurement noise, only the process noise. So this little term is also 0. That's why we could put these two zeros here. And then finally, we multiply these last two terms together, and you get this, because there was a transpose there. And this little expectation by our system model is something we know. It's the covariance of the measurement error. And this term here, this expected value, was by definition the covariance of the error of our estimate prior to us processing that measurement. So we have this little equation here. It's kind of messy. Everything in here is a matrix. But we now have a way, we have equations to say once you process a measurement, we have a way to update. We have a way to update our estimate and update the covariance of the error of our estimate. I'll save this for another video. And this will show us, what about between measurements? This will end up showing us that it was unbiased before we got it, before we processed this measurement. Let me stop there.